Okay, in this video, I want to share with you how is this waveform implemented. We will dive into some details of the code. First of all, if you look at it, like the dragging and the zoom in and zoom out is very smooth. And also, if we switch the timeline, like the rendering is very quick. However, it is not always like this. If we go to an earlier version, so if we go to an earlier version, which is like last week, right before our waveform refactor, it is much slower. Okay, now here we have the build of the old version. If we click those timelines, it will not open because the newer version has more data in the timeline. So, so there are some errors. But so now if we just switch between those two timelines, you see every time we switch the timeline, it takes several seconds, like 2 or 3 seconds, for the waveforms to be rendered. So first of all, this behavior has been there since the beginning, but at the beginning I don't really mind. But last week I was very annoyed by this because this is a very fast MacBook Pro M2 chip. I think it should be very fast to generate those waveforms, and especially you consider my audio is not that long, it's only like 6 or 7 minutes. It should be like not immediate, but it should be like less than 1 second to generate those waveforms. That's one problem. The second problem is I'm already in the program. This waveform is already loaded into the memory. Why switching will cause this to compute again? So I want to figure out why I want to solve this performance or user experience issue. But my challenge was I before this point I sort of just AI coded pretty much everything, like 99% or 95% of all the code are AI generated. So then what I realized is, so at the very beginning, AI suggested me to save those waveforms in a customized binary format. At the beginning, I thought, oh, brilliant! That's a very smart idea. We can save those waveforms into those formats. But then I'm like, why do we need to have this waveform cache? Because the only reason that we want to compute the cache and save it on the disk and then reload it back to the memory is that maybe computing this cache is very costly. But that might not be true. You see, in the new version, if you switch the timelines, we don't need more time to load the waveforms. Since I didn't read any of the code, I only know some high-level assumptions. I have to verify those assumptions one by one. The first assumption for the cache argument is that generating the waveform is costly, so we need to cache that. Is that true? I write this test, or I let AI to write this test for me. Here, the test video is a very long video. How long is that? Let's look at it. So this video is like 18 minutes long, so that's quite long. You say it finished in 1 second. Let's run that again. So computing the waveform is not that slow, but if you remember in our old version, even reloading the waveform takes more than 1 second, and also those videos is not like 18 minutes, those videos are 6 or 7 minutes. So ideally speaking, it should only takes like 3 or 400 milliseconds. There are two questions in my mind. Maybe loading the cache is actually slower than just compute the waveform from the source video altogether. And the second idea is, why do we even have the cache and reload it and have all the like bloated code? So I just remove those code and compute the cache when I just start to compute the cache when the program loads. So it's like a lookup table. So for example, now I don't have any timeline opened. You see, it's already in the memory. Why is that? So now the new logic is, why do we recompute the cache and reload the cache every time when we switch the timeline? Why don't we just compute the waveform in the background when the program starts, so that it does not influence the UI? So here I have like 7 timelines. The longest timeline is only like 12 seconds, right? So and those waveforms are computed from the source video. When I drop that 4K video, for a brief moment does not have the waveforms, and then the waveform shows up. So the logic is, first I will check all the timelines and see what source videos are used in those, are referenced, imported in those timelines. And I will compute their waveforms in the background. Since the 4K video was not used in any of the timelines, so the starting up did not compute it beforehand. If you apply it again, it's already in the memory, so I never recompute every time when I switch the UI. Like that is the way I optimized this feature. So I have this doubt, or I have this observation, and then I divide this observation into several different hypotheses. And then if it's a computation problem, I will write a separate and a minimum unit test to verify my hypothesis. And if that unit test verifies the hypothesis, and then I will go to the refactor. Because by that stage, the refactor is usually very straightforward. It's just because we already have the design and the kind of the high level, the global control flow, the data flow structure already established in our mind, so it's very easy to do the refactor. First, I did some simplification of the waveforms, and then I did some file moving around. The idea is I have a cache like a lookup table, and I just push new computed waveform into that. It's basically global structure because this entity is like the top level entity that owns everything. I have a waveform cache that's a hash table of the path of the file and the waveform data itself. And if you look at the waveform data, it's pretty much an array, or you can see this case like a double array. A double array is also an array, right? It's basically that. This data structure is not that optimized because it's double vector, and the vector are variable lengths, so the memory layout is not that perfect. However, that is fine because waveform data itself is slow, so it's very small, hundreds of kilobytes at most, or several megabytes at most. So that is because that's not the audio data; it's just the audio amplitude data. And then I have this cache. So if you look at the cache here, okay, let's look at this one. This schedule waveforms. So basically, this is a function that will run in the background executor. So we have the context, span, and detach. So that is in the background. And then I will generate this cache. It's also in the background, right? Like in the background executor, I will do this async generate waveform, and I get a result, and then I basically insert that result into the waveform cache. So since this is my first Rust project, what I learned is if you want to, because I'm reading this in the UI thread, but I'm generating this in the background task executor, right? So basically two thread. So you need to have this arc. So at first I was like, what is arc? Like it's like, is it like a shape, like an arc shape? No, it turns out it's automatic reference counting, and then that makes so much more sense. So basically this is like a box of smart pointers, and that's how you can have concurrency, but also in a type safe way. And what is this job? So basically this is some like a smart AI design here. Every time when we discover a new file, audio or video file, we just put that in the job. Once that is done, we remove it from the waveform jobs hash table, and we insert it into the waveform cache hash table. I was satisfied with this optimization already. So it's very fast, right? Like, because this is computed in the background on start. Because if you think about it, for example, let's close the program, let's open it again. When I say this and click at that, it takes like 3 or 4 seconds. And by the time I click, or by the time any user can actually click the timeline, the data is already there. So although it might spend 3 or 4 seconds to compute, but like the human finger moves much slower, right? So to the user's perception, this is much faster. And also because I removed the serialization to a custom binary format. So the only time I spent on computation is the waveform generation itself. I don't have this additional binary format conversion waste and the file I/O waste. The lesson I learned here is that if you do not understand the domain as the developer, the AI will at first propose you a solution that sounds so smart on the surface, even a little bit complicated on the surface. Because if we are naive, complicated stuff for naive people, they feel complication means smart, but it's actually the other way, right? Usually simplicity means smart. A week ago, I was just bootstrapping this project and I was learning Rust on the fly. I did not have enough mental bandwidth to actually think about the problem because I need to have a lot of bandwidth to think about the Rust syntax and the GPUI framework. Once I pass that phase, I can look back at the code AI generated and realize, oh, AI is actually tricking me. AI is like those bureaucracy, like they propose complicated stuff to sound smart, but at the end they are just doing you total net harm. Does not mean I'm not going to use AI. It just means even if I use AI is not cheat code. I still need to understand the domain and understand the problem I solve. So that is this devlog. And there are 2 devlogs coming, and it's even more exciting. Okay, see you next time. Bye bye.